This tutorial will show the powerful tools that the CSiBridge program offers for the automated seismic design of bridges. Following the procedures described in the AASHTO Seismic Guide specifications, CSiBridge can automatically calculate demand-capacity ratios, including those for seismic design Category D bridges, and can produce a report containing all design results. The seismic design of bridges using CSiBridge consists of 8 basic steps. A quick overview of these 8 steps is as follows. In Step 1, we construct the model using bridge objects. The focus of the seismic design is on the Bence. These Bence will be isolated by the program when doing a pushover analysis. In Step 2, we determine the ground motion hazard. This can be done by simply giving the bridge coordinates using latitude and longitude or by zip codes. In Step 3, the program applies the dead load to the entire bridge and calculates the crack section properties of the columns. In Step 4, the program calculates the modes, performs response spectra analyses, which then gives the demand displacement values. If the bridge is a seismic design Category D structure, the Bence and foundation are modeled with equivalent loads in Step 5. In Step 6, the program calculates the displacement capacity. Code equations are used for seismic design Categories B and C, and a pushover analysis is performed for Category D. In Step 7, the program calculates the demand-capacity ratios. And in Step 8, a seismic design report is produced. Now let's take a closer look at each of these steps. Step 1, building the model. Our model has 3 spans of approximately 60 feet. Consisting of an 8.5-inch slab supported with 5 39-inch deep precast concrete girders and 2 Bence, each with 3 36-inch diameter columns 26.5 feet tall. These columns could have been fixed at their base, but for our model we are including a foundation consisting of 4-foot thick pile caps supported by 14-inch diameter concrete piles with steel casing. The seismic design feature of CSiBridge is mostly automated. The bulk of the work for the user is in building the basic bridge model. However, building a model is described in detail in other Watch and Learns, so we will go through this first step rather rapidly. Here's how we built the model. We started by going to the Layout tab. The first item is the layout line. We have one line defined. Clicking on the Modify button shows the coordinate stations for the layout line. Our bridge has 2 stations, an initial station at 0 and an end 178.42 feet away. Next, we move to the Components tab and the Properties panel. For materials, we will use 4,000 psi concrete and A615 grade 60 for the reinforcing steel. Check the Switch to Advanced Properties option so that we can review the nonlinear settings for these materials. Next, we move on to the frame properties type. The cap beam, the column, the precast I-girder, and the pile. The BRD sections shown on the list are equivalent frame sections created by the program to represent the combined behavior of the deck plus the precast girders when doing a spine model. The cap beam is a rectangular section 39 inches deep by 42 inches wide. The bent column section was created using the section designer. A right click shows that the section is 3 feet in diameter with 13 number 8 bars for longitudinal reinforcing and number 4 spiral confinement. The girder was created using the precast concrete I-girder form. Note that it is 39 inches deep and 13 inches wide at the top. The last frame section created by us was the pile. We created a round concrete section with a 14-inch diameter. However, the pile has a steel casing, so to account for this, we apply property modifiers to increase the moment of inertias. Now we move on to the superstructure panel and select deck sections. We have a single deck defined. With 3 interior girders and 2 exterior girders, which gives us a total of 5 girders. The girder section is the precast section just discussed. The deck has a width of 38 feet 10 inches and a slab thickness of 8.5 inches. The program takes this complicated cross section and converts it into a single BRD frame section for use when doing spine models. Next, we move on to the substructure panel to review the bearings. We have 2 different bearings. The first bearing is used for the abutments and restrains motion in the vertical direction. The second bearing is used at the Bence and restrains translation in all 3 directions. Next is the foundation spring. We have defined one spring property to be used at the bottom of the bent columns. In this case, all releases are set to free, as we want the forces from the columns to be transferred directly into the pile cap foundation. If we were not explicitly modeling the foundations, we would set some or all of these releases to fixed. For the abutments, we have defined one type. This abutment provides a fixed connection to the bottom of the girders. Next, we will review the Bence. We have defined a single bent for both locations. The bent consists of 3 columns topped with the cap beam we defined. The columns are 26.5 feet tall and use the previously defined foundation springs for the base support. At the top of the columns, all connections are fixed to the cap beam. Next, we go to the Bridge tab. This tab is where we define the bridge object that tells CSiBridge how to assemble the previously defined components into a bridge system. The bridge object assignments allow CSiBridge to isolate the loads and the bents that are used when doing the automated seismic analysis. For this model, we have a single bridge object that contains all of the components for our 3-span bridge. The reference line for the bridge defines the abutment and bent locations. Selecting spans and clicking the Show button, we see that the deck section is assigned to each span with no variation. Looking at the abutments, the start and end abutments are the same. A 2-inch thick bearing resting on a fixed substructure. The bent assignments for each span are also identical. Again, a 2-inch bearing resting on our bent structure. After doing the assignments, it is important to link the model so that all components are included in the model. The superstructure is complete. The only item we have not yet reviewed is the foundation. The foundation consists of 4-foot thick area objects for the pile caps, supported by the pile objects. Note how the bottom of the column is above the area object that represents the pile cap. If we extrude the objects, we see that this is geometrically correct due to the thickness of the pile cap. But because the pile cap is modeled with a planar object, we use a weld constraint to connect the bottom of the column to the center of the planar pile cap. Switching to the Loads tab, we see that for this model, the only static loads we will apply will be the dead and superimposed dead needed for the seismic analysis. We are now ready for Step 2. Step 2 is where we determine the ground hazard. We go to the Functions panel and select the type of response spectrum. Clicking the New button, we see that we have many function choices. We will choose the National Cooperative Highway Research Program spectra. Function values may be determined by the program from latitude, longitude, by zip code, or by user input. We will input latitude and longitude. Note how the spectra values change based on the input. We will set the site class to D. With the determination of the site hazard, we are just about ready to start the automated seismic design. The last bit of information that we must input is the design request. This tells the program what type of seismic design to do. Go to the Design Rating tab, and in the Seismic Design panel, click on the Design Request button. Click the Add New Request button, and note that the bridge object we defined is selected, as our model has only one bridge object. Click the Modify Show button and review the options set by the program. Note that the EQ function is selected and that the seismic design category is set to D, so a pushover analysis will be done. Also note that the entire structure is being used for the gravity load case, that the crack sections will be determined by the program, and that the modal load case will be program determined. Lastly, we need to identify the foundation group because we did not fix the columns at the base. Before we run the seismic design, we will visit the Analysis tab to verify that only 2 load cases currently exist, those for the dead loads. We will return to this panel after running the seismic design. The program will automatically create load cases for all of the other analyses that will be done, including modal and pushover. Now we will start the automated seismic design procedure, which will do steps 3 through 7. This may take some time, as a large number of different analyses are being done by the program. We can scroll through the analysis window to see exactly what the program was doing. First, it applies the dead load case to the entire structure and iterates to determine the crack section properties. Based on the crack section, it performs a modal analysis. With these modes, it performs 3 different response spectrum analyses. Next, it performs a dead load analysis using just the Bence and equivalent loads. Lastly, it performs 4 different pushover analyses. Next, we will return to the Load Case panel on the Analysis tab for a more detailed look at the automated analyses. Note all of the additional load cases that have been generated by the program. The first one represents the results of Step 3, the application of dead load and the calculation of the crack section properties. Dead load is applied to the entire structure along with section modifiers. This load case represents an iterative process when calculating the crack sections. Element forces are determined, crack sections are calculated, stiffnesses are modified, and the cycle is repeated until convergence is reached. The actual crack section modifiers used may be reviewed by going to the Advanced tab and then the Define, Named Property Sets, Frame Modifiers command. Here we see for Bent 1 column 1, the moments of inertia are multiplied by approximately 0.28. The next 4 cases represent step 4, mode extraction, and then response spectrum analysis to calculate the demand values. Note that the modal case uses the gravity deadload case with the cracked sections as the starting stiffness. For this bridge, the program asked for 18 eigenvectors. The number of modes is determined by the equation 12 plus 6 times the number of spans minus 2, but no less than 12. Here are some of the modes calculated by the program. The next case is the response spectrum case in the x direction. Modal damping of 5% is used. The following case is the response spectrum analysis in the y direction. And the last response spectrum case applies spectra in both directions and combines them according to the AASHTO seismic guide specifications that require results to be combined using the 130% rule in each of the major directions. The next case is associated with step 5 and again represents a deadload case, but this time consists of only the Bence and foundation structure loaded with equivalent loads from the bridge deck. Again, cracked sections are used, and this step is needed because the structure is seismic design category D, which means a pushover of the Bence is required. Prior to step 5, hinge properties are calculated for the pushover analysis. The automated seismic design request uses hinge properties based on the AASHTO Caltrans idealized model. Note that the program uses PMM hinges, so properties are dependent on axial force, which varies as the bents are pushed. Because the seismic design category is D, the program automatically performs a pushover analysis on the bents that are part of the earthquake resisting system. These 4 load cases are associated with step 6 and represent pushover analyses in 2 directions on each of the 2 bents. This case pushes bent 1 in the transverse direction. Note that the pushover starts from the gravity case for the bents. The program automatically sets all of the parameters. The next load case is the pushover on bent 1 in the longitudinal direction. The third pushover case is for the second bent in the transverse direction, and the last pushover case pushes the second bent in the longitudinal direction. From the pushover analysis, the program determines the displacement capacity. Going to the display panel and selecting the Show Static Pushover Curve command, we can view the pushover curves for each of our 4 pushover cases. Typically, the displacement capacity is taken as the point on the curve that is located just past the peak base shear, where the base shear is 99% of its peak value. Once the pushover analyses are complete and the capacity displacement has been calculated, the program automatically generates the demand-capacity ratios, which can be viewed by going to the Show Tables button on the display panel and selecting the Bent Demand-Capacity table. Here, for each bent and each direction, the table reports the demand, capacity, and the ratios. The last step is to generate a seismic design report. The program will generate a comprehensive report with a single click. Go to the Design Rating tab and click on the Report button in the Seismic Design panel. The report includes a complete table of contents, images of the model, bridge data, section properties, loads, and all design results. Editing of the report may be done directly by the user. This concludes this tutorial on automated seismic bridge design.